I'm with Erhan, talking about distributed quantum.
Thank you very much. Hello, everyone. I'm a research scientist in the ESNet division. Today, I'm going to present our effort to build a quantum network testbed in the Berkeley area. It's sort of the aerial the picture of our testbed. And this project focuses on distributed quantum computing aspect. And it's carried out in collaboration with several institutions that include UC Berkeley, Caltech, and University of Innsbruck. So in my presentation, first, I will briefly describe the use of quantum networks for scalable quantum computing. And I will introduce the QUANT-NET project and its core technologies. And I will present our progress towards this testbed effort. And I will conclude my talk with a brief discussion of the future opportunities. So let's start with the big picture. As we know that quantum information science promises technologies that offer unprecedented computational power, unbreakable secret communication, and unbeatable precision. So while each of these technologies are progressing independently, one of the ultimate goals will be to combine them and eventually utilize them under a single and preferably global infrastructure, so-called quantum internet. So the concept of the internet, in a way that is similar to the internet that we use in our daily lives, on the other hand, the way that operates is quite different. Realization of a future quantum internet will rely on processing and storing quantum information at local nodes and interconnecting, in other words, entangling distant nodes using single photon level light. So in this, then the construction that we have atoms or atom-like systems just operate as our processing and storage units, and the photons are the carrier of quantum information across fiber optic links, even maybe free space satellite links. So to build this large-scale network, then we have two essential tasks that to distribute quantum entanglement and store it in a way that we can use it on demand. So the question, how do we do it? So we need basically two elements. The first one is light matter quantum interfaces that allow generation of entanglement between a propagating photon and a matter platform. So that basically takes care of the distribution part. We need this hybrid form of the entanglement, matter-photon entanglement. So then we need to store this entanglement in a remote location, as I said, to use it on demand. Then we need some additional techniques that is basically the Bell state measurement, photonic version of the Bell state measurement. So to understand that how this process works, now imagine that we have two light matter interfaces at distance node A and B. And they produce photon matter entanglement, this hybrid photon entanglement. And imagine that it happens asynchronously on those two sides. Then what we do is that we perform these photons coming from each node. We interfere them on a beam splitter. So this is a really simple beam splitter. So then we detect these photons after the beam splitter using this single photon detectors. Provided that these photons are indistinguishable, then we can, in principle, project this initial entanglement, the matter-photon entanglement, now matter-matter entanglement at this nodes. So this is the way that we typically generate the remote entanglement. So basically, light matter interfaces in conjunction with Bell state measurement is sort of the most essential ingredients to build large-scale quantum networks. So the potential applications will be quantum repeaters, long-distance entanglement distribution by repeating this structure, distributed quantum sensing, and distributed quantum computing. In this context, probably one of the short-term applications would be use this networking idea to scale up the quantum computers. The basic idea is to interconnect small-scale processors in a way that we can scale up the computational power. So the basic notion in this idea, then we have now a small-scale processor having good quality of the qubits, high-fidelity qubits, and we dedicate some of the qubits for communication purposes, while other qubits are used for the standard processing task. So then what we do is that we perform this Bell state measurement as I described before to generate entanglement between the remote communication qubits. Once we do that, then we have now the entanglement is ready to use for the quantum computation. So how do we do that now? Remote quantum computation. The whole idea relies on this teleportation, quantum teleportation. So in this process now, what we do basically is that we can encode any arbitrary qubit state to one of the processing qubits that we have here. And we can perform a local entanglement operation between the communication qubit that carries the established remote entanglement and our processing qubit that carries the target state that we encoded here. So then performing after this local operation, we can make measurements, mid-circuit measurements, and it in principle allows teleporting the state from processor A to B. So that's the basic idea. So we can extend this idea to implement remote quantum gates. So now we can have quantum gates implemented using two separate processors, physically separate processor. Idea is pretty much the same, but this time now we'll be performing entanglement operations between two local entanglement operations between two processing qubits in separate processors. And then this will allow us to implement this C0 gate, for example, as shown here. So now quantum state teleportation and gate teleportation or non-local gates are the basic ingredients to build universal distributed quantum computing. This is sort of what we would like to explore in our testbed effort. So in our testbed, we have 3 nodes. They're all in the Berkeley area. And two of them belong to trapped ions, and one of them is for color centers like the in silicon photonics. But in this talk, I'll mainly focus on the trapped ion nodes. So the nodes are connected with deployed fibers underground, a few kilometer length of the fibers. The advantage of this platform is that they are good processing devices, but also they can be used for the networking that basically makes them really good candidates for distributed quantum processing. So
A and B.
Where's the A and?
A and B, you had a picture with A and B before.
So A and B will be here then, yeah. So this is the quantum node technologies that we are focusing on, and we have also quantum frequency modules. Given that the photons emitted by the trapped ions are not in the telecom wavelength, so we basically convert these photons that near infrared range to telecommunication photons using these quantum frequency conversion modules. And the third thing is that we have this quantum network control. Basically, we would like to go beyond physics experiments and then do this networking in a scalable and automated fashion. That's basically we are developing a network control plane. And I will briefly summarize these components, especially the trapped ion part. So as I mentioned, trapped ions are really good candidates for distributed quantum computing for 2 main reasons. That's sort of obvious reason. One of is that they have already, they are native candidates for basically with optical interconnect. They have strong optical transitions that can be used for building light matter interfaces I described in earlier. The second reason is that trapped ions platform is one of the leading quantum computing platform. It has excellent processing capabilities. So with these 2 reasons that there has been significant effort towards fulfilling the requirements of the distributed quantum computing. That includes the high rate, high fidelity entanglement, remote entanglement generation, while we can store long-lived entanglement in sufficiently long time. So, and it has been shown that this process can be done in separate experiments, and it has been even demonstrated that we can have very good indistinguishability between the photons that we interfere on a beam splitter, and then this could be used for quantum teleportation and non-local quantum gates. And early even this year, it has been reported that this idea of the distributed quantum computing could be used that actually to run a quantum algorithm, just like as I described before. So what we want to do then in Berkeley to add a new dimension to this, to make everything that I mentioned here in a scalable manner. So The specific approach that we are working on is this new trap technology that I call 3D printed microtrap technology. So just to give a little bit background, historically, the ion trapping just started with kind of, relatively bulky traps that are shown here, like the pole traps. And they are really very good in terms of the trapping capabilities, but on the other hand, these kind of systems are not scalable. So the community more evolved towards this surface trap, the planar trap, that allows us scalability, but we start losing the superior trap properties of the bulky trap. So what we would like to do is that to use this 3D printed technology developed by the Hartmut Hafner's group at UC Berkeley to combine all the superior features such that we can have this scalable distributed quantum computing as our main goal. So if you just look a little bit more what this kind of trap will bring to us, that's like we expect that we can have high fidelity and the high rate local and remote entanglement due to the two main reasons that comes associated with this trap. One of them is that we can have very large trap frequencies compared to state-of-the-art technologies because of this 3D geometry, microgeometry, meaning that this trap frequencies allows us to have the energy spacing of the motional state much larger than the state-of-the-art system. So this then leads to have much lower heating rates. This is one of the decoherence mechanisms in the ion trapping systems. So other important features that we can have very tight confinement. So this is very important because all this single photon generation process relies on excitation with strong optical pulses that it can induce some motional, excitation. So with this tight confinement, we can mitigate this to a great extent. So this can allow us, in principle, high fidelity local and the remote entanglement, as I mentioned before. In addition, the large trap frequencies that can allow us to have the cooling only based on the Doppler cooling, the laser cooling. We may not, in principle, go to this more complicated or time-consuming the ground state coolings. That's one of the advantages that can allow us to have some high rates. And in addition, with this high trap frequency, it's possible to transport the ion faster than the state-of-the-art systems that could be used for multiplexing that I will be describing in the next slide. And also this 3D geometry allows us to have larger optical space, meaning that we can interface these systems with optical cavities to enhance the rate of the entanglement. So with that motivation to use this 3D trap in context of quantum networking, we have some plans that we have two basically separate labs, that A and B that I mentioned here. So especially at LBL, we just start from scratch almost 2 years ago. We established the lab and then we were able to successfully trap the ions using this new technology. So at high trap frequencies especially. And then we also we demonstrated the basic coherent operations and the single photon generation. Our next step currently to interface to this trap with an optical cavity, which is in near concentric configuration. Without going too much detail, we expect that this can allow also very high rate photon extraction from this system, and it's very important for scalability. So while we are, working on this lab establishment and the first experiments that we actually utilize the Hartmut Hafner's lab, which is quite established, to explore the concept of the multiplexing, which is another key feature to have a scalable distributed quantum computing. So in particular, we studied the fast shuttling of an ion chain to demonstrate multiplex photon emission from multiple ions. So in our particular demonstration, proof of principle demonstration, what we did is that we were able to trap 9 ions in a chain, and we used a simple excitation scheme to produce single photons, but by addressing single photons, the single ions at a time in this chain, just like as shown here. So once we produce a photon from a target ion, then we move the entire chain by changing the axial confinement voltages. So then we repeat this process one by one, such that we were able to produce the photons in a multiplexing manner from 9 ions, as just shown in this plot here. So that's also an important thing, that we did this transport like the less than 10 microsecond per site, basically, between the ions. So beyond that, we demonstrated this is indeed working as a single photon source, the multiplex single photon source. We follow the standard way, perform this second order correlation measurements, simply look at the correlation after a beam splitter when it's ideal single photon that we expect to be 0, but it should be also in general much lower than 1. And as you see is that here we have in this shuttling case, this value cross correlation function is much less than 1, suggesting that we have really multiplex single photon source could be used to enhance the entanglement rate in principle 9-fold, as we have 9 ions. So we also benchmarked the quality of the single photon source by comparing this measurement with respect to single ion, no chain, and the ion in a static chain. And then we got a little bit degradation, as you see in the G2 value, but we attribute this problem to just the addressing crosstalk between the ions that when we shine this addressing beam, which could be easily mitigated. So the cause of this fast ion shuttling in this case was the heating. So this is like if we don't have shuttling, we can see the Rabi flopping, the qubit, driving just very nice. But after finishing the shuttling, as you see that the Rabi oscillations just damp very quickly, especially at the full speed. The reason is that, as I mentioned here, that we use actually the existing traps relying on the pole trap. So that's basically not really suitable for fast operation, given that the trap frequencies are really relatively small. So what we want to do in the next step is that use our 3D trap, implement this scheme such that we can have now the order of magnitude larger trap frequency, and we expect to eliminate this damping in the next implementation. So the second technology that I wanted to mention is that the quantum frequency modules that to convert the ions frequencies, the photon frequencies from 854 nanometer to telecommunication wavelength. The idea is relatively well developed, relying on the quantum photonic techniques, difference frequency generation. So basically we have 2 nonlinear crystals, and we combine coherently our input photon at 854 with a Planck field at 1900 nanometer. That's a very strong Planck field. What it does with that, well, after this, the nonlinear conversion process, we can have at the output our single photons at telecommunication wavelength. The energy is given by the difference of these energies of the photon. So the important thing with this conversion technique, it has been proven that it can have very low noise operation, and as well as it can allow us to preserve the polarization, meaning that it can be used for polarization encoding scheme, which is very popular in the domain of the quantum networking. So currently we implemented this idea. We have around 10% efficiency, but mainly this system efficiency comes from the lossy components. What we believe that we can increase our efficiency up to 40% range for the experiment that we will be doing this year and next year. So the final element that, as I mentioned, that we would like to go beyond this physics experiment, have all this network operation scalable and also automated fashion. With that motivation, our engineering team has developed this quantum network play. So there are 2 essential components in that network operation that we developed. One of them is that the processing nodes, that basically processing devices, need to be controlled in a real-time fashion. So that's basically, we provide that with the FPGA-based real-time control at the nodes. So in addition, that to preserve the indistinguishability between the photons that we interfere, we have to have the time and the frequency synchronization, as well as to calibrate the polarization across the link. So our software control that illustrated here, that allows this non-real-time calibrations and at certain times. And on top of this, users can make some requests on our system such that they can actually access our devices and even can generate entanglement on demand. Just early this year, we actually demonstrated this. We had to showcase this feature in San Francisco with a live demonstration of the on-demand single photon generation. While our systems are just like Berkeley lab and the UC Berkeley, this is sort of showing the kind of the on-demand single generation experiments that made by the users. So as a sort of the final thing that I would like to say, now we have all these pieces coming together, and then we are in the last phase of the project. Now we are really working hard to combine all these layers such that we can demonstrate this the basic element teleportation across 5-kilometer fiber link. And in the future, beyond this project, we have two sort of the directions. One of them that we would like to understand the requirements for the distributed quantum computing in terms of the resources and algorithms and all different aspects. In this regard, we work with Katie and the Nurse Quantum team and also collaborate with Quora. The other direction is that in parallel that we would like to extend the number of nodes and then use this networking idea for different quantum computing platforms that include neutral atoms and the superconducting devices. And then with that, maybe we can demonstrate the prototype operation of a future quantum internet in the Berkeley area. Thank you so much.